Welcome to the Masterclass 2021. We will be talking about trending topics in geospatial technology. This has been organized by Sakhi Regional Group of Asia, Women in Geospatial Plus, in collaboration with African Women in GIS and GeoLadies Philippines. Our mission in Women in Geospatial Plus is to build an inclusive global community, uniting, inspiring, and empowering all women plus in geospatial sector to become strong leaders and change makers. We inspire, unite, empower, and choose to challenge the status quo. We offer advocacy, community building, events, mentoring, and a speaker database. In advocacy, we have more than 18,000 followers. We feature women who inspire the community every week on our social media. We have a vibrant community on Slack channel with more than 2,500 members. Even you can be a part of this by joining the Slack group. We host monthly webinars on career development. This is the mentorship program where we make a living by what we get. We make a life by what we give. This is well said by Winston Churchill. So in this, we offer one-to-one and group mentorship. In 2020 and 2021 cohort, we had 115 participants from 34 countries. Stay on to this. We will give you more information towards the end of the program. We have a speaker database, which we have a wonderful speaker database through which we provide an opportunity for talented women speakers to represent us in conferences and webinars throughout the world. This is a program which we have initiated this year. These are the marvelous ambassadors who represent various regional groups. This is the hierarchy of the regional ambassador group. Hello, I am Dr. Laxmi and Goparaju, Scientific Advisor, Vindhyan Ecology and Natural History Foundation, Mirzapur, Uttar Pradesh, India. I am the Regional Ambassador for Asia, Women in Geospatial Plus, and founder of Sakhi Regional Group of Asia, which is a platform for online learning for female geospatial enthusiasts. You can find me on Twitter at @Laxmi Goparaju. I hope to bring together students and professionals under the Women in Geospatial Plus to promote learning and interaction. We welcome volunteers to be our country ambassadors. You will be the national point of contact for your country if you fit into the role. Join us and grow your professional network. Register for our speaker database. Put yourself out of the comfort zone. Get mentored or be a mentor. Speak for yourself and diversity and be a factor of change. We have many plans, but we cannot have an impact without you. Let us make a change together for us and for the future generations. The objectives of the masterclass are: this masterclass is for the women plus enthusiasts for geospatial technology. The pandemic has made life tough, especially for women. We aim to enhance the capacity of women and underrepresented young people so as to make them more self-reliant in the days to come. We are starting with the beginner level introduction to various trending topics of geospatial technology like Python, drones, etc. A list of resources would help to dive deeper into the topic as per your interest and convenience. Your feedback is valuable to us for further improvement and would help us in coming back with more topics which are career oriented and will strengthen the professional capacity. Our speakers for the master class are Aisha, Brenda, Crystal, Gala, Laura, Lay, Lake, Maeve, Sabrina, Sharon, and others. Thanks. If you have any questions, you can mail us at sakhigeo@gmail.com, or you can post your questions in our Slack channel. This is day 1 of the masterclass, and we have 2 topics to discuss today. One is Google Earth Engine, an introduction, and the other is NASA Data Resources, a compilation of open data resources.
Hi everyone, nice to meet you. I'm Sabrina Szeto. I'm a geospatial consultant based in Germany. And today I'll be sharing about getting started with Google Earth Engine. So today we'll be talking about getting started with Google Earth Engine. And there are a couple of things that we're going to cover. So first we'll start with some background about what Google Earth Engine is, why even use something like that, some data models for working in Earth Engine. Then we'll take a look at the JavaScript and the Python APIs for actually using Earth Engine. I will introduce a few web applications that can be built using Earth Engine, and then give you some next steps for what to do to start learning how to use the platform and some resources that you can access. So we live in a time when there's just an amazing amount of Earth observation data being produced every day. According to some recent statistics, about 150 terabytes of data for the Sentinel program is downloaded per day. And when you look at NASA data, about 102 terabytes are downloaded per day. So there's a lot of people trying to access this data, process it, analyze it, turn it into useful information that people can use. However, it's often more efficient when we move our questions and our analyses to the cloud than to actually move the data down. So instead of focusing on downloading the data, Earth Engine actually lets you type a very short script, make a few steps for processing the data, and then run the analysis on the cloud. So what they've done is they've ingested over 30 petabytes of Earth observation data, everything from Sentinel imagery data to meteorological data to population gridded data. A wide variety of data is available, and you can click on that link there to search and take a look at what's available on the dataset catalog. We also have this immense power from the Google computational infrastructure that allows us to do parallel processing and basically speed things up tremendously. So instead of now downloading one satellite image onto your laptop and then working with that, as many of you might have done as students, you're able to now do everything on the cloud without having to download anything until the finished product is ready. So here are a few examples of animations, time series animations that have been created to show changes around the world. This shows growing and retreating glaciers and ice over the year. You can see rivers meandering, changing their course over time, and cities growing. You can see rapid urbanization and changing of land cover from agricultural to urban. You can see deforestation actually happening live, where tracts of forest are cleared for agricultural purposes. So Google was able to process this data. It would have taken them over 2 million hours of computation, but because they were able to use 66,000 computers, they only took 1.5 days. So that was one of the products, time-lapse, which was created early on, processing the Landsat archive. So that kind of gives you a taste of the power that's possible on this platform. And so now we're going to dive in and take a look at some of the data models that you'll need to understand before you can start using the Earth Engine platform. So the simplest data model here is a geometry. If you're familiar with vector data, these refer to basically different types of shapes. There are points, lines, and polygons. And it just stores a shape in the form of a series of coordinates. So when you add information or properties to the geometry, you then have a new data model called a feature. So one example on the right here are the Nature Conservancy ecoregions, where each shape, which is an ecoregion, contains properties such as the type of ecoregion, perhaps. So now each of these are features. Then we also have raster data in the form of images, where you have a stack of georeference bands, which can be a satellite image or meteorological data, where each pixel has a certain value that stores a number. And each band has its own mask, projection, and resolution data as well stored in it. And it also contains a list of properties such as the date the image was taken or the bounding box for where this footprint of the image sits. So those were individual elements. You could think about them that way. And when you put them together, you actually have collections. So you could have a feature collection, as I showed you before with the ecoregions. That's a feature collection of ecoregions. And if you have a collection of images, such as all the Landsat 5 images taken in a certain year, those could be stored as image collections. So when you think about desktop GIS, when you're looking at a shapefile where you have a row representing a certain feature, in this case, this is the US census tracts. You have a shape, the geometry information is stored in one column, in the shape column, and then you have these additional columns where you have other properties such as the geo ID or the name of the census tract and so forth. So this is what it looks like in the desktop software. But when you think about it in Earth Engine, a feature collection basically looks like this. When you print it, it tells you, in this case, it was limited to 50 elements in the feature collection. And when you expand a feature, you see similar properties here, like these columns. So there is a geo ID, like this one had, and there is a name. There's a name here too. So in this case, it's pretty similar. It's just displayed a little differently. So that's something you have to get used to. So the map-reduce paradigm is what actually makes Earth Engine so powerful. The first part of this, the map portion, talks about applying a function to each element of a collection. So we're going to do the same thing to all the elements in our image collection or our feature collection. So for example, if we're thinking about the ecoregions or the census tracts, maybe you want to compute the area of each census tract or ecoregion. And instead of having your laptop do this one feature at a time, you're able to split the problem up over many, many different machines in the cloud and have each one of them solve just one problem. So each of them computes the area of one feature. So, it will take much less time because they only have one task to do. So that's the map portion of this paradigm. And then when you look at reduce, you then aggregate everything back into one answer, so to speak. So for the example of the features, now that we have calculated the area of all the features of our census tracts, we can sum the area and get like a total, a final answer for what is the total area of all these features. And if you were thinking about images, you could calculate the cloud cover for each image, and then you can also create a median pixel composite after, say, you have done some kind of cloud masking on each image. So you map a cloud masking algorithm over all the images in your collection, and then you create a median pixel composite where you basically stack the images together and you take the median pixel off that stack and use that to build a composite over your area of interest. So that will be the reduce portion of this paradigm. So now that we've covered some technical basics about the data models and the map and reduce paradigm, let's take a closer look at what it's like working in Earth Engine. So the great thing about this geospatial platform is that you can do everything from pre-processing, analysis, and visualization, all in the same place. Obviously, there are always pros and cons for using different tools. And the nice thing about Earth Engine is that you're able to do a lot of the image pre-processing in the cloud without having to download large amounts of data. So you can do filtering, masking, creating mosaics. And then when it's time to do some kind of analysis, for example, perhaps you're interested in calculating certain land covers based on some classified land cover, or you're interested in doing some vector operations, creating buffers around streams, you can do that in Earth Engine as well. You can also do time series analysis because you can, at a certain point or in a certain region, create a time series chart of changes in NDVI over time, perhaps. You can actually upload training data and do some kind of image classification. One example I've seen, someone used OpenStreetMap data to classify urban pixels in a location. There are also now more advanced algorithms such as object-based segmentation. I've seen examples which have created segmented fields using the segmentation algorithms available. And now there's also an increased connection between Earth Engine and TensorFlow. So you're actually able to, in addition to the basic machine learning algorithms like random forests, support vector machines that are in Earth Engine, use TensorFlow and neural networks to actually do more advanced machine learning. And then last of all, the Earth Engine team has really invested a lot of time to build up the visualization portion of the platform over time. You're able to not only create maps, as I will show you later, but you can also visualize data in parts, applications that you can then share with us so that others can access your data, download it, create their own visualizations or analyses. And now that it's has a growing integration with the Google Cloud Platform, you can also do even more advanced app building outside Earth Engine as well. So we're going to start with the Python API. And this is the link here if you're interested in installing it. So you can either install it on your laptop, or you can also use Colab. So the first package that would be really interesting is Gmap, which is a Python package for interactive mapping with Earth Engine. And it's developed by Qiusheng Wu. And as you can see, it allows a lot of functionality through the Jupyter Notebooks platform. It allows you to basically code iteratively and see the results of what you're making as you go. So if you're interested, definitely check out those links there. Watch some tutorials which Qiusheng Wu has created on YouTube. So the next interesting plugin is with the QGIS open source platform. You can actually connect Earth Engine with QGIS using the Python API. And check out those links for a few examples for how to do that. And this was developed by Hennedy Donchitz. So the JavaScript API is probably the one that most people are familiar with. And it's also really popular because you're able to access Earth Engine in your browser without downloading anything. All you have to do is go to a certain link, log in, and then you can start doing your analysis. So this is the basic layout of the code editor. And I will point out some important areas here, and then we can take a look at the actual code editor itself. So there are two main portions here. There's a map below, which allows you to visualize the results of your analysis. This central panel here is where you will be typing in most of your codes, your scripts, loading, examples, and so forth. And then this panel here on the top left is where you have access to your scripts, documentation, which is very useful for searching when you're getting stuck on something, as well as your assets, things that you upload like shapefiles or images or CSVs. And then on the right-hand side, you have another 3 tabs. The first one is the inspector, which allows you to click on a point and inspect a pixel. The second one is the console output, where you can print and see the results of, say, the elements in your feature collection. And then the tasks tab allows you to run tasks that you have created. So now let's take a quick look at the actual code editor. So I'm logged in here, and you can zoom in and out in the map window, change the background. You have also access to geometry tools, which allow you to, on the fly, draw simple geometries, which can be useful for creating training data sets or selecting areas of interest. Up here, you can actually search for data. So for example, if you're interested in Sentinel data, Sentinel-2, you can easily click on the data set of interest. When a window pops up, there's a short description. You can take a look at what the band names are, what the resolutions are, properties of the image. And then when you want to bring this collection into Earth Engine, you can either copy the name of the collection here, or you can click on import, and this goes right in here. And then you can change the variable name to something else. So for example, I'll change this to Sentinel-2. So the quickest way to get started is to head into the scripts tab here and take a look at one of these examples. So we're going to pick something simple. Let's take a look at this Landsat for cloud masking example, and then all you have to do, and this progress bar here sort of tells you how things are going. And then as you wait and see, the results get loaded in the map window. So this is an example of cloud masking. What's happening here is the image is, you're taking the pixel quality band from this multi-band image. And then there's a bit here which tells you, which basically stores which bits are cloudy. And then this is mapped over, then a mask occurs where you're masking all the cloudy pixels. And then this is mapped over the entire Landsat collection, which has been filtered to this start and end date. So 1st of April 2010 to 30th of July 2010. And then basically this is stored as a function. And then here is where we actually execute everything. So this cloud mask function is mapped over the entire collection that we have chosen, filtered to these dates. And then a median composite is made. So the last bit here basically tells the map where to set the center of the image. And it's then added, the composite's then added to the layers here. And turn that on and off. And then this gives the visualization information red, green, and blue, bands 3, 2, 1 for basically a natural color image. And this sets some gamma for basically how this appears. So, or values really, the min and max values. So if you have a script like this and you want to share it with someone, you can get the link and you're able to copy this, email it to somebody, and when they load it, they can also see what you have created. So that's for sharing your scripts. You're also able to turn this into an app by clicking on the apps button, and you can share these apps with other people as well. So that was a really quick fly-through of how to load a script, hit run, and have some of the results visualized. Definitely look in here, click on the different docs, learn about them, and I encourage you to really explore how to use this JavaScript API. All right, let's switch back to the presentation. So I showed you how to create an app. Let me show you a few actual examples here. So these two links are great resources for checking out different apps that have been gathered, both from the Earth Engine development team, as well as Philip Gartner has also created a wonderful gallery of Earth Engine apps. Here's one of the earliest apps, the Global Surface Water Explorer, shows a data set that was created on Earth Engine. And this app allows people to turn on and off different layers, download the data sets, and visualize it, panning around to areas of interest, zooming in and out. And this is another app that was created by a colleague of mine. This is the Global Surface Urban Heat Island Explorer. And as you can see, you can have a legend in the app. He has a drop-down menu which allows you to show different data variables. And there is a time slider bar here, which allows you to move it back and forth to change the year that the data to be displayed is from. And if you click on an urban center, you can actually have statistics appear. So a chart will appear with some statistics. So this is the Global Population Explorer, and similar to the last app I showed you, if you clicked on a country, it would be then added to this bar chart here, and it will show you the total population of that country. You are also then able to display the results as a table, or if you click here to expand, you can actually download the data as a CSV. So that was a really quick fly-through of some apps that you can play with later on. Now let's take a look at some next steps for you to get started using Earth Engine. So the first thing you need to do is go to earthengine.google.com and sign up for an account. So Earth Engine is free for non-commercial use, educational use, and research. So definitely welcome everyone to sign up and start learning. So after your account has been approved, you can then take a look at some of the great video resources as well as tutorials that have been created already. So here are links to a couple of tutorials as well as videos that you can watch. There are also are created by members of the community that have code snippets as well that you can follow along. And then these three links here are great sources of material from the Geo for Good Summit as well as the Earth Engine User Summit from the past few years. So these are actually really cool because there are all these great workshops focusing on specific topics, such as building your first app or uploading your own data to Google Earth Engine, or doing some kind of image classification that you can watch the video, work through the tutorial at the same time. And these are very valuable workshops that you can go back to. So as I showed you before, there are a lot of amazing example scripts available in the platform already. And to start with, you can simply look in one of those tabs, take a look at a script, and if you're building your own workflow, don't start from scratch. See how something has been done before and use those example scripts as building blocks for you to create and modify your own analysis. And if you're stuck, here's where you can find some help. So one great source of information is the Google Earth Engine API documentation. There are oftentimes script snippets available that you can copy and use. There are tips available for how to understand how things are working. And that will be my primary place of reference. Then the next place I would recommend to go to is the GIS Stack Exchange. Over the years, there's now been a great body of questions and answers that have built up. So you're able to Google a question and go to the Stack Exchange site and get the answer. So that's very helpful. And then the third source of information is the Earth Engine Developers Forum, which is a Google group that you can definitely sign up for and search, because other people might have had the same question as you in the past. Search for the keywords that you have, search for the question that you have, take a look at how other people have approached the same problem. And oftentimes people also share scripts that they have written and where they've gotten stuck. So it's a very helpful source of information as well as experience over time. And we're now doing a lot of things virtually, so I encourage you all to think about also joining the next Earth Engine virtual meetup. We meet once a month. It's a user group where different users can feature their own work and make presentations and share their knowledge. So we are taking the summer off and we'll be back online again in September. Then on Twitter, there's also a really great lively community of people who are posting tutorials, tips, and so forth. Check out the hashtag Earth Engine, and you'll be able to find many of these accounts and users. And then lastly, there's going to be an opportunity to join the Geo for Good Summit, which will be online this year. It's going to be from the 14th to 17th of September. So keep an eye out for when the announcement goes out that you can apply. So that's a very quick run through of getting started with Google Earth Engine, and I'm happy to take any questions. All right.
Thanks, Sabrina, for that rundown of Earth Engine. That was an amazing presentation. We do have a couple questions, not too many. You answered a bunch of them at the end, so
Great.
But I'm gonna recap a few of them here. You mentioned the videos and tutorials, and one person asked, do you know of any cheat sheet guides for beginners to work with scripts in Google Earth Engine? Some of what you just went over might be a little bit intimidating, especially for folks who are used to working with imagery or data, but maybe still don't quite dive into that kind of coding level of expertise,
Sure. So there is the Beginner's Cookbook is a community tutorial that is available on Earth Engine. If you click on that link to the community tutorials, it's one of the ones that's featured on the website. And if you look at the Geo for Good Summit, there's a breakout session called, I think, Earth Engine 101 or something like that. So that's one that beginners are definitely recommended to take a look at because it goes through everything in a reasonable pace. And by the end of that session, you'll have started working with your first script and seen the results. So it's definitely a great way to build your confidence in using the platform.
Next question here. What kind of projects have you done yourself with Earth Engine, and what were your favorite data sets to work with?
So I've done a wide variety of projects on Earth Engine. It's one reason why, in general, I love the geospatial world so much, because you can work with all kinds of questions. So some past projects I've worked with included doing some land cover classification for a certain type of vegetation, to calculating distances from roads to understand how habitats of a certain endangered bird would be affected, to looking at imagery from Sentinel-2 changes over time, to see how constructions of certain infrastructure have occurred. So it's a wide range of topics that you can work with in Earth Engine.
Great. Another one here, it's a little bit of a different one. Can you go into how you store your data in Earth Engine to work with Earth Engine datasets? Is that taking advantage of other Google Cloud services available, like Big Data Query, or or just Google Drive separate than the cloud services? How does that work? How does Earth Engine interact with some of maybe your personal stored settings that Google allows? Or is it unique?
So every Earth Engine account has something called an asset manager. So there's a fixed amount of space in there. I think it's 250 gigabytes, I might be wrong, but you're able to upload that amount of data directly into Earth Engine. It could be CSVs, shapefiles, your own imagery. So that's one place to store it. Our Google Cloud platform for storing your assets. So that's another option. And when you are exporting data, say you've done your analysis and now you want to extract like a finished composite, for instance, you can then export that either directly to your asset manager. If you want to use it in another script later, you can export it to your Google Drive. So you're limited by how much space you have in the drive, or you can export it to the cloud, and as in the Google Cloud platform. So those are the three places you can export stuff.
So if you have more than a gig of data, because some people want to have spreadsheets or dealing with hundreds of thousands of points, if not millions, and that would quickly exceed that storage that you recommended. So what would be a good solution to deal with more than a gigabyte of data?
I think there's, I don't remember what the actual file size limit is for the asset manager, but it is quite large. So even uploading a gigabyte of data might be possible, if I recall correctly. But definitely using the Google Cloud, like GCP, would be the way to go if you're working with that, that size of data.
Now, Google Earth Engine itself has grown tremendously over the years in terms of its advocacy and use cases. Where have you seen the most growth where people are using it right now?
So I would say that initially a lot of the uptake was amongst educational and research institutions. But now with the advocacy that's going on and the interest that's going on, I think there's a growing uptake as well in the public sector, as well as nonprofit sector, where people have questions about, say, environmental or socioeconomic concerns, such as crop yields, and so forth. So it's really exciting to see how the use cases have expanded over time.
Absolutely. Well, I want to appreciate your time with this. And I like to give everybody a chance to do this when I interview, but any last minute plugs that you want to give for the community, Earth Engine, or any activities that you have going on personally? So I guess from me, on behalf of many users, I think a lot of us are very grateful that Earth Engine is free and is still free for non-commercial use. So we hope things stay that way. And once again, I welcome anyone who would like to learn more about Earth Engine to join the Earth Engine virtual meetup. We'll be starting back up in September. We have a link now. We're trying to get people to put in their availability, so we picked the right time where most people can join us. So yeah, I hope to see more people join the meetup in the future. That actually brings one last minute question that just popped onto the side as relates to what you just said. So, I'm a huge fan of Google Earth, and Google has a habit of, have these waves of support for their geospatial services, whether, you're not sure if something's going to stick around or not. And Earth Engine has been an incredible resource. Google Earth has been as well, and we've all been nervous about the community, but in my personal hope is they connect more services from Google Earth itself to Earth Engine and have some more deeper tie-in there. Not just the web client, but also the thick client, which is still supported because a lot of those services haven't migrated yet. But the question here on the side that just came in is, what services or what features do you hope Google comes out with to support and help innovate Earth Engine in the next year or two?
So before I answer that question, I'd just like to say that I think there actually is a way to publish Earth Engine data into Google Earth. So there is that link there. And right now, with the development of the further connection between Google Earth Engine, the Google Cloud Platform, and with TensorFlow, I foresee that there will be, and BigQuery actually, I foresee that there will be this move towards having really large data users use more of the GCP services, and in so doing, create a revenue stream for Earth Engine so that it can continue to be supported as a service. So that's the good news there. And in terms of new features, I would definitely be happy to see even more development of the apps, the web applications that you can build on top of Earth Engine, in particular with respect to the charting and plotting capabilities. I think more advanced data visualizations that are in the form of charts and plots would be very helpful for some of the apps that people want to build.
That's an awesome response, and hopefully someone out there in Google's listening. But aside from that, I appreciate your time with us and talking about Earth Engine once again. I'm Adam Simmons with Project Geospatial with the Geospatial Frontier Virtual Technology Fair, and we're here with Sabrina Szeto and talking about Earth Engine. Thank you, everybody, for listening.
Thank you so much, Adam. This has been wonderful.
My name is Leah Schweizer, and I'm a member of the NASA Earth Science Data Systems GIS team. Today, I want to provide an introduction to NASA Earth Science, showcase some relevant data and content, then transition to discovering and accessing and using the data, highlight some resources to get started, and also provide an invitation for engagement. Most people associate NASA with outer space, but NASA also gathers information about the Earth from a fleet of satellites. This information helps us to map the connections between our planet's vital processes and the effects of ongoing change. A multitude of data is collected to fuel this research, and that data is freely and openly available to anyone. Seen here is the NASA Earth fleet. This slide shows the operating satellites in blue and green, those in development in purple, and those in planning stages in yellow. NASA Earth Science oversees data centers which are dispersed around the country and archive 16 terabytes and distribute 32 terabytes of information products each day. This data comes from the spacecraft as well as field campaigns and collected over many years to support NASA Earth Science research worldwide. I'd like to highlight some critical Earth observations of interest that will hopefully be valuable to this community. An important note is that these are largely global satellite collections, so the spatial resolution may not meet your needs, and the underlying data files are often in NetCDF or HDF, which may not always be GIS ready in your primary tools. The Terra and Aqua combined MODIS land cover type data product provides global land cover types at yearly intervals. The Harmonized Landsat and Sentinel-2 project provides consistent surface reflectance data. The combined measurement enables global observations of the land every 2 to 3 days at 30 meter spatial resolution, much higher than existing layers. The data product is also provided in Cloud Optimized GeoTIFF or COG format. An important note is that this data is provisional, so has not yet been validated for science quality. The MODIS land surface temperature layer shows the temperature of the land surface, which differs from air temperature as it provides the temperature measurement of whatever is on the surface, for example, bare sand in the desert, snow or ice, a leaf-covered tree canopy, and even man-made buildings and roads. The sea surface temperature layer is a level 4 analytic product from NOAA, which is based on observations from several different instruments. These products date back to 2002. So you can also perform temporal analysis by comparing data across the years, for example, 2002 to 2020, as seen here. The Integrated Multi-Satellite Retrieval for Global Precipitation Measurement, or GPM-IMERGE data, estimates precipitation over the majority of Earth's surface in half-hour, daily, and monthly intervals. Here we see GPM precipitation accumulation using the one-day early run algorithm, which is updated every 3 hours. And here we see the GPM-IMERGE data as seen over 4 days. DAYMET is a North American data product derived from daily meteorological observations used to produce gridded estimates of daily weather parameters. This includes minimum and maximum temperature, precipitation, vapor pressure, radiation, snow water equivalent, and day length. DAYMET also provides long-term data sets of continuously gridded daily weather variables to help us improve the understanding of terrestrial ecosystems. The Global Ecosystem Dynamics Investigation, or GEDI, offers products measuring canopy height and can also be used for vertical canopy structure and surface elevation. NASA's Soil Moisture Active Passive, or SMAP mission, allows us to detect how much water there is in the surface layer of the soil. Values here are symbolized to identify low or dry conditions as brown and high or wet conditions as green. Transitioning now to human impact. These anthropogenic biomes describe globally significant ecological patterns that are caused by sustained direct human interaction, to include agriculture, urbanization, forestry, and other land uses. Now that humans have fundamentally altered global patterns of ecosystems, forms, and process, these new biomes provide a contemporary view in a human-altered form. The Socioeconomic Data and Application Center produces collections of data focused on human impact. This includes the gridded population of the world, which is now in its 4th version, and models the distribution of human population, both counts and densities, on a continuous global raster surface. The Global Human Footprint Index represents the relative human influence in each biome expressed as a percentage. The purpose is to provide an updated map of the impacts on the environment. The Global Man-Made Impervious Surface, or GMIS dataset, comes from Landsat data consisting of global estimates of fractional impervious surface cover and consists of global percentages as well as per pixel associated uncertainty for the global impervious cover. The Global Grid of Probabilities of Urban Expansion presents probabilistic forecasts of global urban land cover change from 2000 through 2030. Satellite images of Earth at night, often referred to as nightlights, provide the clear yet composite view of patterns of human settlement across our planet. These black marble layers show the visible light emanating from city lights and other human-driven patterns. This layer is an overlay showing only the nighttime lights, stripping out other natural light sources. So on the right, you can see fishing vessels, as well as the obvious border of South Korea. What I just showed you was a lot, but that was also just the tip of the iceberg. There is a lot of data available to enable science to better understand our planet. So now I'd like to transition to how you can discover, access, and use NASA's Earth observation data. Most of what I just showed you comes from Worldview, which is a visualization application that provides the capability to interactively browse full-resolution satellite imagery layers. Many of these imagery layers span many years and are updated within 3 hours of observation, essentially showing the entire Earth as it looks right now. You can search and add layers via thematic areas or science disciplines. Within Worldview, you can view data over time and also compare data sets. So here we see the mammal species richness data with the MODIS global land cover type data. The land cover imagery shows 18 land cover types, while the mammal richness data shows the number of species in a particular class, family, or threatened category. If you want the raw data, NASA data is freely and openly available. Earth Data Search provides the means for discovering, filtering, visualizing, and accessing all of NASA's Earth science data holdings. This includes more than 33,000 Earth observation data collections. Here you can search by topic, collection, or place name. NASA also utilizes Esri's ArcGIS Online, which is a collaborative web GIS allowing users to create and share data, layers, maps, applications, and analytic products. We have over 1,700 content items that are publicly available, ranging from web services, dashboards, notebooks, and story maps. Selected content is also being nominated to Esri's Living Atlas of the World, which now features 16 imagery layers provided by NASA Earth Data. Esri has also curated layers attributed to NASA, and seen here are a few examples of content that Esri has enabled using NASA Earth observations. These are typically time-enabled image services, which you can then view and pull into your own application, such as a desktop tool, including open source tools like QGIS. If you use Google Earth Engine, you'll search and find many NASA data products available in their catalog as well. Also included is curated content provided by Google. This interface also accommodates the direct add of both data files and web services, and from here you can enable analysis and then share your science. The bottom two screen grabs are from NASA's Applied Remote Sensing Training, or RSET program, which hosts webinars and are a great resource for capacity building. A few other tools to access and use NASA's geospatial data includes Appears from the Land Processes DAC, which offers a simple and efficient way to access and transform geospatial data from a variety of federal data archives. Appears enables users to subset geospatial data using spatial, temporal, or other parameters. And this utilizes GIS server technology to enable a single point of access to all services, distributing a wealth of data. The Alaska Satellite Facility focuses on synthetic aperture radar, or SAR data. Vertex is their search tool, which allows for the preview of numerous types of SAR data. It also offers on-demand processing of radiometric terrain correction. ASF also has several data recipes and an ArcGIS Python toolbox for integrating and analyzing SAR data in your GIS. Oak Ridge National Lab's Spatial Data Access Tool, or SDAT, is an OGC-based application to visualize, download spatial data in various user-selected spatial and temporal extents, file formats, projections, and web services. So we understand NASA data can be complicated. You might be feeling a little overwhelmed. So I want to get you some help in getting started with learning about NASA data and GIS tools. So the following are a few great resources. If you're new to using NASA Earth Science data, Pathfinders are the perfect place to start. Pathfinders focus on key themes and are intended to familiarize users with various datasets that are applicable to a certain study area. They offer guidance on resolution and provide links to data sources. A Pathfinder specific to GIS provides a guided walkthrough of NASA data and GIS tools. It links to the tools from which data can be visualized, subset, and downloaded, as well as offers a brief tutorial on using tools to access NASA's geospatial web services. So following along, you're able to create the same images as seen here. Also relevant to this community is the Pathfinder focused on biodiversity. Data toolkits are for more proficient users who know what they're looking for. They're designed as entry points to access NASA Earth Science data resources and are organized by topic. Here you can find links to datasets, tutorials and how-tos, feature articles, user profiles, as well as other useful information. The Earth Data GIS page provides much of the content just reviewed and also links to more tutorials, guides, data recipes, and also projects related to GIS at NASA. The NASA Earth Data Data discovery and access webinars span the earth science disciplines and are designed to help users learn about NASA data, services, and tools. As the monthly webinar schedule varies, be sure to check out the online catalog for upcoming events. You can also search previous webinars by entering a keyword, an instrument, or mission, or even a science term. Earth Data Forum is a tool developed to engage subject matter experts from several data centers to discuss general questions, research needs, and data applications. So here you have the capability to search by discipline, major project, and services or usage. Users can query how to access, view, and interpret the data, alleviating that time and energy of working with the data to instead focus on the research and analysis aspects of your science. We also recently contributed a chapter in Esri's GIS for Science, Volume 3, highlighting the use of NASA Earth observations to map wildfires, drought, flooding, and rising temperatures. There's also a publicly available online companion, which is full of resources. So now that you've heard from me, we'd love to hear from you. Feedback from user communities is extremely valuable. So understanding your data needs to include what format, distribution method, and what application or tool you use to work with the data will help us improve our services. The URL here is a link to a very brief questionnaire that we'd love for you to fill out if you have time. We're also teeing up a new initiative focused on uncovering needs to broaden outside use of NASA data, or Unbound, targeting new users who aren't currently using NASA data but have a valid requirement or use case to explore. Additionally, if you're interested in funded research opportunities, I'd encourage you to check out the programs listed, which focus on harnessing NASA data to advance our understanding through application, tools, and technologies. These are just a few places to get started on exploring with us. Thank you for your time.